Hey, Vlad here, devinsidey.com. Welcome to another video. I made a video a month ago or so about dependency inversion where I explained the benefits of dependency inversion or the inversion of control. In this video, we're going to take a slightly more complicated example, but it's going to be a very realistic one, and we will see how the object-oriented paradigm implements the inversion of control. I'm also going to create a separate video about paradigms, which will probably use parts of this video. All right, let's see what OO has to offer. Oh, hold on. Sorry, I forgot that I have an announcement to make. This video is scheduled to come out on May 6, 2018, and my very first video just happens to have come out exactly 1 year ago, on May 6, 2017. Look how nervous I was. I think now I'm officially 1 year on YouTube, and in order to celebrate that, maybe you guys could just go to my very first video and give it a few likes, just for fun. All right, now let's get started. As always, we have Sublime on the left and we have SBT on the right, running in the terminal and running our code. Now, in this video, we're going to take a bit of a knowing approach. I'm going to introduce a problem, and then we're going to try and experiment with different solutions until we finally arrive at an optimal one. I could have made this video only like a few minutes long and just give you the final solution, but where's the fun in that? So just bear with me. So remember how in this video about dependency inversion, we use higher order functions to implement the inversion of control. So we're basically just passing around pointers to functions to other functions, right? And by the way, the link to this video is going to be in the YouTube cards. So let's start with this example. It's going to be similar to the one in the other video. So we're just going to have one function f, and it's going to be a higher order function. So as a parameter, it's going to take a function g, which is going to take an int and produce a string, right? And the whole function f is going to return a unit. All it will do, it will just print line g, and it will give it as argument 1337, right? So now let's implement g. So we have def g, which takes some number, right, and produces a string, right, because it has to match this signature over here, right? So it produces a string let's do something fancy. So let's do console magenta, which is my favorite color, which is why most of the channel is styled like this. Magenta plus number converted to a string, and let's also reverse it just for fun, and let's not forget to reset the whole thing. Okay, so now let's just call f with g as a parameter. So just as a refresher, when the code arrived here, it print line whatever g returned was an argument of 1337. So 1337 was here, it was converted to a string, then it was reversed, so it became 7331, and then we prepended those ANSI codes, and this is why it turned magenta. So the example in this video is going to be similar to this, but it's going to be more complicated because we're going to convert to function f that right now takes only one argument, g. We're going to convert it to a function that takes 3 arguments, and this is going to be the problem that we want to solve. So instead of just passing g, let's also pass in I don't know, this is going to be like super random. So we're going to pass also h, which is going to take I don't know, a string and produce a string. And I'm sorry guys, I'm still sick. Like sometimes you might notice I'm sort of gasping for air. All right, so we're going to take an h, takes a string, produces a string, and we're also going to take an I, takes a string, and produce a character, for example. Right, so what it will do is it will compute the result of g, which is a string. It's kind of funny because now it spells g string, and it will just call g the same as before with 1337. Then it will calculate the result of h, which also produces a string, right? So g produces a string, h produces a string, this one. Okay, so we're just going to call h. And as a parameter, we don't have to, but just for fun, we're going to pass in the result of g. Okay, and now we're going to also calculate the result of I, which is a string. So we're going to call I with the result of h. So we're basically chaining functions together. And as the last thing, because we need to return a unit, we're just going to print line the last result. So we're just going to print out the result of I. That's what we want to do. Okay, so now all we need to do is we need to add those functions. So we already have g. Let's make it a bit more simple. Let's remove this coloring stuff. Let's still do toString and reverse though, and add h. So we have h, which takes some string and produces some string, right? So we'll always have to match the signature. So g is a function from int to string, which is why we have int to string here, h string to string, so which is why we have string to string here, and we're also going to have I, which is going to take a string and produce a character. Okay, so I don't want to make this too complicated, so I'm just not going to do anything in h. So I'm just going to return the string as it comes in. It's also known as an identity function. So if the function doesn't change the argument at all. Okay, so what's left is I, and I takes in a string, and it somehow has to produce a char. So what we're going to do is we're just going to take the first character, and we're going to make it a bit more fancy. So we're just going to say, okay, so string is not empty, then take the first character, and remember the strings are 0 based, so the first character is 0. This is a syntax, right? So I'm going to leave a comment, the first character. Okay, otherwise just return a question mark. Okay, so basically if the string is empty, we're going to return a question mark. And now all we need to do is we need to call f with g, h, and I. That's a copy paste mistake because I actually returns a character, and we're seeing here that it returns a string. So we have a character over here, and let's run it. Okay, so what's happening here is as soon as we pass 1337 to g, g is going to convert it to a string and to reverse it, right? So the return type, not the return type, but the return value over here is 7331. H is an identity function, so it's just gonna return 7331 as is, okay? And I is just gonna take the first character, so which is why we're seeing the character 7. Now, the same problem also applies to classes. So what we're going to do is we're just going to wrap this function in, with a class. So we're going to have a class around it. We're going to call it f, okay? And it's going to have, as its body, it's going to have f. So let me move it to the right a little bit. And we're just going to take all the arguments that were being passed to f, cut them out, paste them as the arguments for the constructor, okay? And we're also going to return f to do stuff, okay? So now over here, we're going to first create an f, new f, we're going to pass g, h, and I, and over here, we're going to call do stuff. And the result should be exactly the same unless I made a typo somewhere. No, it's exactly the same. Now, we sort of jumped into this thing that accepts multiple functions as arguments. But what does it actually mean? I mean, obviously it means still dependency inversion, right? We still have an inversion of control. But apart from that, there's another important aspect of that. So what we see here is a so-called code smell. So the code is trying to tell you that those three things, G, H, and I, that they somehow belong together. And recently we learned about the environment model of computation and about message passing style, and we're slowly tipping our toes into object-oriented programming. So all of this combined is a shiny new hammer, the shiny new organizational hammer, and it's starting to feel like we've found some nails. So if you have a function in your code that accepts multiple functions as arguments, they probably, very likely, belong into a class. So let's convert this whole nonsense into something that you can imagine a bit better, and then it will become obvious how G, H, and I belong together because they will be simply named properly. So the example that we're going to go with is an example of electric devices. So we're going to have a few electric devices like a TV or a light bulb, and we're going to have a class which is going to become this one that is going to be called energy meter, and its job is going to be to turn some device on and to start measuring how much energy it consumes, and then there will also be a way to retrieve this data from the energy meter. So let's get started. So let's just as a first step, let's just convert f to energy meter. So now we're gonna do this, and let's call this f, let's call it energy meter. So now still obviously it doesn't measure anything because we just renamed a few things, okay? So let's create the scaffolding for the energy meter. So first we're gonna remove G, H, and I because we're not gonna use them anymore, and because this code is not gonna compile anymore, I'm just gonna comment it out. We're also going to remove do some stuff, and as parameters we're also gonna have three things, but they're not gonna be called G, H, and I, and they will not have the same signatures, okay? So the first argument is going to be called watts per second. So how much our devices how many watts they consume per second. And it's a simple integer. And the second parameter is going to be a function called turn device on. It will not take anything as its argument, and it will produce a unit. And the third one is going to be a similar one. It's going to be called turn device off. So I'm just going to copy that, paste it over here, and I think I pasted it twice accidentally. Oh no, I didn't. Okay, it's all good. Okay, so turn device off. We don't need this comma over here. Okay, let me actually move this up because the line gets kind of longer. Move this down, and my experience tells me that we need 131 hyphens. Okay, so all this function will do, the public API, I'm sorry, this class, the public API of this class is going to be two functions. It's going to have start measuring, which is just returns a unit, doesn't take anything but returns a unit. And as of right now, it will do turn device on, right? And we're gonna have a similar one that is still in the opposite, sort of, right? So we're gonna have stop measuring, and we're gonna have turn device off. So now let's create something like a TV. Okay, so over here, we're just gonna have, let me have a comment, something like a TV. Let me remove the cursor. Okay, so we're gonna have watts per second of TV, which is an integer, and this is just a random number from my head, so we're just gonna have, say, 500. Okay, and we're gonna have a turn TV on function, produces a unit, and you know, this is just a simulation, sort of. So as of right now, we're just gonna say, okay, TV is on. But in reality, if this was like a real production application, this code will actually turn some TV on. Okay, so we have TV on, and we're also gonna have TV off. Turn TV off, which just prints out TV off. Okay, and now in order to construct the energy meter, and okay, let's just do this first. So instead of G, H, and I, we have watts per second. Watts per second equals watts per second of TV, comma. Then the second argument is turn device on. Turn device on equals turn TV on, and turn device off equals, hold up, like this, equals turn TV off. And as the example, we don't have the function do stuff anymore. So what we're gonna have is, we're just gonna say start measuring, right? And then we're gonna block the current thread for a second, and then we're just gonna stop measuring. And let's see. Okay, so it seemed like it worked. Obviously, as of right now, the energy meter doesn't measure anything. It just turns the device on and it turns the device off. Also, we have a deprecation warning. So it says there were two deprecation warnings since Scala 2.12.0. Rerun with deprecation, which is a compiler flag for details. Okay, so all we need to do now is we need to go to build SBT. And we need to tell SBT how to pass flags to the Scala compiler. And we do this by adding this one line. We can say Scala C options plus equals, which means add to the option. So colon equals means just set the value, but plus equals means add to the already existing options. And what we need to pass in is a string with this option. So if we just go here, and I'm just going to copy that, paste it over here, right? Now, if I press enter here to interrupt the continuous compilation loop, we're going to reload the project. And once it reloads, we do run again. And now we see the actual warning. And it tells us that the add expansion of zero argument method values is deprecated, right? So we have a zero argument method over here. And over here, we're trying to convert it into a function like this, right? So it used to work, and in Scala 2.12 it still works, but a deprecation warning means that in the future versions of Scala, it will not be possible anymore. So this code will not compile anymore. And in order to avoid that, we're just gonna do the add expansion ourselves. So we're just gonna have a function literal here that just calls turn TV on, the same thing over here, right? And now we should have the warning should be gone. Okay, so now there's no warning anymore. And because I know that by the end of this video, we're going to use also a few more flags, which you could pass in like this. So Don't forget the empty lines. The empty lines are important. So you can have some other flag here and some, yet another flag like this. Or you can just put them all into a sequence and do this instead. So you can do a Scala C options, and now instead of plus equals, hold up, there's a typo somewhere, options. So instead of plus equals, we can say plus plus equals. And what we pass in is not a string, but we pass in a sequence of strings. So we just do sequence, and now we can pass all of them in. So we can do this, and then just comma, the next one, right? Which is a bit shorter. So as for now, we're gonna stay with one, but I'm gonna use keep using the sequence syntax, because I know that by the end of this video we're gonna add a few more flags. So let me remove these. Okay, we'll still need an empty line over here. Actually, let me remove the empty line to show you what's going to happen. So let's reload the project, and now it's going to say, end of file expected, but a semicolon found. So you don't see a semicolon here, but it's getting injected by SPT, right? But if we have an empty line here, and we can say retry, so R stands for retry, and now it should be fine. Okay, so now we're in the project again, we run again, and we still have our example where the energy meter turns the TV on and off. Okay, I'm gonna leave it as a tab here, but let's go to main. Okay, so technically we don't really need to implement the energy meter in this video, because this video is about dependency inversion and how the object-oriented paradigm implements dependency inversion, but there is no fun in having it not actually doing anything. So let's actually implement it just for fun. Okay, so we're going to go to the energy meter, and the first thing that we're going to do is we're going to have a private instance variable. So we're going to have a private this variable, and we're going to keep track at what time the device was turned on. So we're going to call it turned on at millis. So we turn the device on at what time, and the value is going to be milliseconds, and it's going to be a long, and in the beginning it's going to be a 0. So now every time we turn the device on, when we start measuring, we're just going to set this value. Hold up. Oh, come on. Don't autocomplete the wrong one. Okay, so we want to pass in, and there's a way to retrieve the current milliseconds from the 1st of January from 1970. So this is a very common thing in programming. It's been decided at some point that the time we basically count milliseconds since one very specific time in our history. It's the 1st January of 1970. I believe. And so most programming languages have a way to retrieve the milliseconds since then. And in Java or Scala, it looks like this: system current time millis, right? Which is milliseconds since January 1st, 1970. All right, which doesn't really matter in this case, but it's definitely a topic for another video. Okay, so and when we turn the device off, right, we're going to do a very similar thing. So we're just going to remember the time when we turn it off. So we want to calculate the duration in millis by measuring the time again when we turn it off, and just subtracting what we accumulated. Subtracting that thing, right? So by having this difference, we basically have the duration in milliseconds. And because we have a watts per second, or watts, I think they pronounce watts per second, we also need to convert, we need to work around with, we need to work with durations in seconds as well. So what we're going to do is we're going to have duration in seconds equals duration in millis, convert it to a double, and then just divide it by 1,000. Because 1 second, because there are 1,000 milliseconds in a second, right? And then every time we stop measuring, just for now, we're just gonna print it out: duration in seconds. Okay, so now because we're blocking the thread for 1 second, we should see something like 1 second here. Sometimes it will contain 1.2 or 1.444 something, but it's always going to be around 1 second. So it's not like very precise. But we're not actually interested in the duration. We're interested in how much watts it consumed, right? So all we need to do is, instead of printing out duration in seconds, we want to print out watts per second, multiply with the duration in seconds, and now we have watts. All right, 500. And the other thing that we want to have from the energy meter is we want to be able to turn it on and off a few times, and we want to see that it accumulates the energy consumed in total, right? So if we do it right now, So if we just copy that, right? So we just add a print line and we'll let it run for another second. It should tell us that it consumed 1000 watts, but it didn't, right? It's not gonna do this because it doesn't remember what it consumed. Okay, so this is what we're gonna build now. Okay, so we're gonna have a function, not a function, we're gonna have another instance variable, which is going to be private to this instance, and it's going to be called underscore what's consumed in total, which is going to be, oh come on, which is going to be a double. Okay, and in the beginning it's 0. So now instead of just printing it out, before we're gonna put it into this variable. So over here, instead of just printing it out, we're gonna do this equals watts per second times duration, right? Which is wrong, right? So as of right now, it's wrong, but we're getting there slowly. So now we just basically sort of refactor the code a little bit, but it's still wrong. So it still does 500 and then does the 500 again, and it's because we're sort of forgetting what has been accumulated so far. So by adding this tiny plus, which is just a syntax sugar for this, right? And Scala will do this for us. Introduce those parentheses, but still I prefer to have them. So this is just syntactic sugar for this, right? So the next what's consumed in total is whatever the current is plus the new calculation. Okay, so let me remove that, and now we should see 500 and something close to 1000. Okay, 500 and something close to 1000. And the last thing that we're going to do is we just want this method to stop measuring. We don't want it to print out this thing, right? So we want to sort of let it do one thing. So what we're going to do instead is we're going to expose this what consumed in total as data. So we're going to have a def here that is just going to be called exactly like this, but without an underscore, right? Returns a double, and all it's doing is it returns this. But this one is private, which means that we can only write to it and write and read to it from this current instance, but from the outside we can also access this guy. Okay, so now all we need to do is we need to remove this print line, and we need to sort of move it to over here. So after we stop measuring, we're also gonna do print line energy meter dot, how did I call it, what's consumed in total, and we're gonna do the same thing over here, which is just a refactoring. The next thing that I'm going to show you is sort of like an addition. It's a sidebar. It's not really vital for this video, but I sort of forgot to explain this in the video about message passing style. So there's a really cool syntax to get rid of this underscore even inside of this instance. So outside of the code right now, everything looks fine. So the client code looks fine. It says energy meter dot what's consumed in total, but inside of it, we're still working with this underscore, and there's a way to mitigate this. So the first step to do this is we're just gonna copy that. No, actually without the colon. We're just gonna have another function called exactly the same, and it's going to get the new value, which is a double. It returns a unit, okay, and all it's doing is it assigns a new value to this variable, right? So equals a new value. So now instead of this, right, we can say we can just call this function, right? So we can do this, and then the value is what's consumed in total plus, it's basically the same as before, watts per second times duration in seconds. Right, so but it didn't really get better, because before it looked actually kind of cool, but there was just this tiny underscore that we wanted to get rid of. And the way you do this in Scala is that if you have two functions that are called like this the same, and one sort of just retrieves the data and the other one changes it, right, then if you call it with an underscore equals, right, so you need a pair of having them be called the same. And if you call it with underscore equals, and let's fix the code over here like this. So as of right now, we didn't change much, but now because it's called like this, then we can use the same syntax as before, but without the underscore. So basically, it will convert this line into this line. And actually, let me write it like this, so that it's a bit more clear. Hold on, let me duplicate that. Like this, right? So it will basically, it will when it sees a line like this, where you're sort of like assigning a new value to what's consumed in total, but what's consumed in total is a method that is called very specifically. It has this underscore and equals, right? And there is also another daf called like this that gets the value. Then it will convert this line, or this line, which is just yet another syntactic sugar, into this line, which is kind of cool. Okay, so if I did everything right, it should work. Yeah, so it works the same. We have 500 and 1000. And now the last thing that we need to do is, so now this method is publicly available. So all we need to do is we need to protect it the same way as we protected the others, right? So now it's possible to do this trick only inside of the class, which is cool. By the way, in the programming terminology, this method is usually called a getter or an accessor, and this method is usually called a setter or a mutator because it mutates some variable. Okay, so the energy meter is ready now, and it's actually really beautiful. Now it's not perfect because it makes some assumptions about the devices. For example, it makes the assumption that the energy meter is the only thing that is in charge of the device, right? So because what could happen is that we start measuring, and something behind our backs, that has a pointer to the device, that it actually turns the device off, and then we will still keep measuring, right? So this is a very interesting conversation. It's a very interesting discussion, and there are many ways to mitigate this issue, but it's a discussion for another video. What we want to do now is we want to get back to the dependency inversion by adding new devices. So what we're going to have now, so we already have a TV, and what we're going to have now is we're going to have something like a light bulb. So I'm just going to copy that, paste it over here. So now we have something like a light bulb, watts per second of light bulb, which is probably less. I don't know how much less, but let's just do 100. So now we're gonna have turn light bulb on, and just gonna say light bulb on. Over here we're gonna say light bulb off, and over here we're gonna say turn light bulb off. Okay, so as of right now we can, so we're still passing the functions from the TV, but now we can actually use these ones. So let's replace them. Let's take this one, let's take this one, and let's take this one. So now it should be something around 100 and something around 200. Okay, so this is a dependency inversion, right? So the energy meter does not need to be changed if we add new devices, which is really, really good. But this doesn't solve our original problem. So we want to combine them into one thing. So instead of passing around three things all the time, they obviously belong together. So what we want to have is we want to wrap a class around them. So we're going to have a class called TV. So instead of something like a TV, we're actually going to have a class TV, and we're going to have an open brace here, closing brace over here, and move that to the right. And we're going to do the same trick for the light bulb. So we're going to have a class light bulb, open brace over here, closing brace over here, move all of that stuff to the right. And now we're going to create a light bulb over here. We're going to do light bulb, which is of type light bulb equals new light bulb. Okay, and now we're going to do light bulb dot all of this stuff. And we already know this. That's how it works. So now the idea is that we sort of need to change only one thing instead of three things when we're passing in a different device. So let's try that. So let's do, instead of light bulb, let's do a TV. So we're going to have a TV here. We're going to have a TV here. And now everywhere where we say light bulb, we're going to say TV. No, that doesn't compile now because TV does not have a function watts per second of light bulb, right? This is very easily fixed by just introducing the same naming convention, right? So we're gonna have just watts per second. We're gonna have turn on, and we're gonna have turn off, and we're gonna do the same thing over here. So instead of having this, we're gonna have this. Instead of this, we're gonna have this, and it's just going to be watts per second. Did I do watts per second? Yes, watts per second. And the same thing for the TV. So just going to be called turn TV on, turn on, turn off, and just watts per second. So now it should work. Okay, so we can pass in the TV, everything's fine, but we can also just replace the TV with the light bulb, and it should also work, which is kind of cool. Okay, now it's getting better. So we need to change only one thing, but did it really get better? We're still passing 3 things around instead of just one. So what ideally, you know, what we want to have is we want to pass like one thing. So object orientation looks at this and says, no bueno. So if you want to stay faithful to object orientation, we need to figure out a way how to pass around one thing, right? So we already have a TV and we already have a light bulb. Why can't we just pass a TV or a light bulb straight to the energy meter? So what we want is we want an alternative way to construct the energy meter. So if we look at the energy meter, in its constructor, it accepts those 3 functions. And what we want to have is we want to have an alternative way. And the way we do this is by introducing an alternative constructor. And the syntax for this looks almost like a function, but without the return type, and it has to be called this. So in the body of the energy meter, we're going to say def this. And instead of those 3 things, it will take the device in, right, which is going to be a light bulb, right? And there's no return type because it will just construct the energy meter always, so there's no need to specify anything. And then we're going to have an equal sign. And in the body of this constructor, we're going to call the primary constructor. We're going to call this one, right? So we're just going to do this, right? And it has 3 parameters. So watts per second is going to be device dot watts per second, comma. Now turn device on is going to be device dot turn on. And as we have seen before, we need to do this so that we don't get the warning. And the same thing is going to be for turn device off, which is going to be turn device off like this. So let me also do this and also do that, and it should all still compile exactly you know, and work exactly the same way because we're not trying by now to pass in a device. So now if you scroll down to the energy meter, so instead of doing all of that, we can just pass in the light bulb directly. If I could type light bulb, there we go. So now we're passing the light bulb directly. It gets passed into this alternative constructor. The alternative constructor rips out the functions out of it, passes them to the primary constructor, and this is how the whole energy meter is being created. So the functionality is still the same. But now we have a problem. This thing wants a light bulb. So when we try to pass in the TV instead of the light bulb, it's not going to work. It's going to say, found a TV required a light bulb. So how can we convince the type system that a TV is somehow similar to a light bulb? And we're going to find out the proper way by the end of this video. But as of right now, we're just going to reduce the type safety a little bit, which is something that we usually don't want to do. So instead of this, instead of getting the light bulb as a device, the type of the device is going to be absolutely anything. Right? So if we do this, though, it's still not going to compile because anything does not have the necessary things, right? It doesn't have the watts per second, it doesn't have the turn on, it doesn't have the turn off. So what we need to do is we need to figure out which kind of device we have in our hands, what is a type of device, and only then rip out those functions, even though they're called the same. So what we're going to do now is we're going to try to figure out the type, but this is actually not going to work, right? So it's not going to work in this so-called auxiliary constructor, but we're still going to type it out and then we're just going to move it. So what we need to do is the first thing is we need to surround the whole thing with curly braces, okay? And then as the first line, we're going to say if device is instance of light bulb, right? Then do this. Let's move it to the right. Then do this. First thing is then let's actually have a light bulb of type light bulb, right? And let's take this device and convert it. So we're going to say as instance of instead of is instance of, and convert it to a light bulb, right? So we're basically converting an any to a light bulb as soon as we know that it is actually an instance of light bulb, right? So now instead of device over here, we can use light bulb because any did not have those necessary functions, but a light bulb actually does. So we convinced the type system that this thing is actually a light bulb. Now we're going to copy that, and we're going to say else, and then paste now. Actually, hold on, let me paste it like this. No, that didn't help. Okay, else if, so if the device is a TV, sorry, not like that, TV, convert that to TV, then rip out the functions that, you know, they have the same name, but we still need to do this whole dance to rip them out. Okay, and otherwise, as the very last thing, so otherwise we're just gonna say not a device. The problem with this is that even though this is a correct code, the only thing that we can do from an auxiliary constructor is actually just call the primary constructor or some other auxiliary constructor. So what we need to do now is we just need to take this def out and just put it in some other component. So what we're gonna do is I'm gonna cut it out. I'm gonna cut it out so the energy meter looks the same as it looked before. And now underneath, we're just gonna create some component, and we're gonna paste it in. And we're not gonna call it this. We're gonna call it static dispatch. And by the end of this video, you're gonna find out why. Static dispatch. And what it returns is it returns the energy meter, right? So now it returns the energy meter. So now instead of calling this over here and over here, we're just gonna construct a new energy meter, right? So now the code still doesn't compile, okay, because at the bottom we're still trying to construct an energy meter by passing it a TV. But what we want to do now instead is we want to do some component dot static dispatch, and now we're going to pass in the TV. And now I believe if I did everything right, now everything works. And also we can replace it with a light bulb and it works again. The problem that we have now is that we lost the dependency inversion, right? So if we look at the energy meter, it sort of looks like we solved the issue, right? So it doesn't matter what we pass in, it's still gonna work. So every time we create new devices, every time we add new devices, we don't need to change the code of the energy meter. So we still have the dependency inversion, we still have the inversion of control, so everything is still fine. But is it actually really fine? Because what we did is we just moved it out into some component. So basically right now, every time we add a new device, we would need to also change this code. We would need to add this pattern match to this code over here. And by the way, Scala has a very beautiful syntax for pattern matching, which is something that we're going to do first. So we're going to have a separate video for pattern matching alone because it's a very slightly bigger topic. In fact, we started talking about it in the previous video. So in the previous video, I said that every time you make a decision based on one thing, and in this case, one thing is just a device, then you can use the pattern matching syntax. Also, before we do this, just real quick, we also lost the type safety, right? So now what we can do over here, so before we change everything, I'm going to have a class whatever, right? Let me move it down over here, right? So we have a class whatever, and I'm gonna have a whatever new whatever, and now I can pass in whatever to this thing. It's gonna compile, and it's only gonna crash at runtime. It's gonna tell me it's not a device, right? Because our static dispatch says at the very last case, so if it doesn't know which kind of device it is, it just assumes that it's not a device. Okay. So let me revert that thing. So I actually want to have this whatever. No. Okay, so we're passing in the light bulb. Everything is still fine. So all we need to do now is we need to let me scroll down here as well. So yeah, everything is still fine. So all we need to do now is we need to go to the static dispatch and improve the syntax a little bit because I want to show you this syntax. So all we need to do is we need to say device match over here, and then we're going to have different cases. So this is going to be one case, and this is going to be another case. Okay, and the last one is going to be this case. And every time after cases, this is going to be the default case, arrow to the right. So if none of the cases match, then we're still going to do this. And over here, we're just going to copy this, right? And we're just going to say, so if this is a light bulb over here, then do this code. And now over here, we already have an instance of the light bulb. So all we need to do is just this, and we can remove those empty lines. And the same thing we're going to do here. So we're going to do the TV. We're going to put it over here. We're going to have, whoops, over here. We're going to have an arrow to the right. We don't need this anymore, and we don't need those braces anymore, right? So it kind of looks more beautiful, right? So we're passing a device, which we pattern match on the device. So, okay, so if it's a light bulb, then this thing is instance of and as instance of in one thing, which is really cool, right? And then it's available over here. So light bulb TV over here. Let me save, and actually let's see if I made a mistake. No, I didn't. So it actually looks more beautiful, and we can actually improve it a bit more if we renamed some component to energy meter, and thus create a companion object for the energy meter, right? And rename this static dispatch to apply. Then now instead of doing some component dot static dispatch, we're going to do energy meter dot apply. And we learned in the previous video that whenever a class or an object has a method apply, we can just skip it. So now it looks basically like a constructor for an energy meter, right? So it looks like we're doing new energy meter light bulb and new energy meter TV, right? So it works with a light bulb and it works with a TV, which is kind of cool. So the syntax it really got better, but our problem is still not solved. I mean, look at this, right? So we sort of lost the dependency inversion, and we're still lost, you know, a bit of type safety, right? So we can still pass in whatever, right? So it's just syntax is better, right? We can still pass in whatever, and it's still going to crash at compile time, and this is not what we want. Let's start getting closer to an actual solution. So instead of passing 3 things to the energy meter, what we want to do is we want to count out all of them, and we want to put them into a separate data structure. So we're going to have a final case class device, right? And they will come in as parameters, right? So it's going to look like this. In fact, let me actually do this and that. Okay, so now it looks a bit more beautiful. Okay, so and now we can just pass in the devices over here, and instead of doing turn device on, we're gonna just do device dot turn on, and the same thing for turn off over here, right? So this is going to be off, and the last one is watts per second. We're going to do device dot watts per second, and because it's a function now, we have to use the parentheses. All right, so let's see if it compiles. It shouldn't compile as of right now. Actually, it doesn't compile because I wanted to have 3 functions. So watts per second was supposed to be a function that doesn't take anything and produces an integer. In fact, maybe let's do this like this. Okay, so now it should be a little bit better. Yes, it's a little bit better, but we still have errors. Okay, so the few errors are saying basically over here that turn on is not a member of a device. It's because I forgot to rename them, right? So instead of you know, we want to call turn on here, so it's gonna look like this, and we're gonna have turn off. It's gonna look like that over here. We're still going to have compiler errors, but we're getting closer, right? So as of right now, we have only 2 errors left, and this should be at the place where we're constructing the energy meter in the static dispatch. So it turns out that we actually we don't want to have the static dispatch anymore. So let's just comment this whole thing out, okay, like that. So now it says not found value energy meter, right? Because we just commented it out. So what we need to do now is we need to say new energy meter, right, and pass it in the device. But now it says, okay, I found a TV, but I want a device. So what we need to do now is we need to do something similar to the static dispatch, but we can distribute it, right? So it's not one place that where things need to be added every time we add a new device. We're just gonna have a function on the TV and on the light bulb. It's gonna look exactly the same, and it's gonna be called toDevice. Right? And all we'll do is it will construct a new device. We can construct it without the keyword new because it's a case class, right? So we're going to do watts per second equals this watts per second, and we're going to do turn on equals this dot turn on, and the same thing for turn off, right? So we're going to have turn off. And we're going to have exactly the same function on the light bulb. So we're just going to copy that and put it here. So again, it's pretty much exactly the same thing as in the static dispatch, but instead of being at one place, every time you add a new device, you just include this teeny tiny thing that can convert a light bulb into a device or a TV into a device. So now if I did everything right, all we need to do, it doesn't look like I did everything right, because this is a function, right? I keep forgetting that this is a function. It doesn't take anything and returns this, and now we need to fix it over here as well, like that. Okay, so now we're back to the same issue, but now we can just say dot to device. And now it's going to work for the TV, and it's also going to work for the light bulb. Now this is cool. So now we don't have the problem with the static dispatch anymore, that we can pass in whatever, and it's going to compile, but only crash at runtime. And we have the dependency inversion back, right? So every time we add a new device, we just add this tiny little snippet of code at the same place where we add the device, right, and not at this top level component. So we don't need to change this top level component, which was doing the static dispatch, right? So now everything sort of got better, but it looks like we sort of arrived at the same spot where we started, right? Because even though we sort of have this device, but we're still passing like 3 things around, right? It's like a freaking curse. How do we get rid of it? And the way we get rid of it is by doing the following. Let's go to the device, wherever it is. It's over there. Let's not have it as a data structure. So let's have it just as a regular class, right? And it will not have a constructor with 3 things. Instead, it will have, I'm sorry, I wanted to replace this brace with this one, like this. So instead, it's going to have 3 variables, not vals. They're going to be variables, okay? And the signatures are staying exactly the same. And now we just need to put in some implementation. It doesn't really matter what we're going to put in here, as we will see in a few seconds. So this is going to do this, and this is going to turn the device on. So I'm just going to put in turned something on, and we don't need the comma anymore. And the last one, so let's do this as also like this. Turned something off. And now when we convert things to the device, right? So in the to device thing, what we're gonna do is we're gonna first surround it with curly braces. We're going to create a device equals new device, and then in the end we're gonna return this new device. But before, so instead of constructing it over here, right, we're just gonna say device dot, right, like this, and everything else should stay the same. Let me copy that and put it into the light bulb. So what it's doing is it creates a device with mutable variables inside of them. Then it sets them all to the implementation of the, in this case, the light bulb, and in the other case, to the implementation of the TV, and then it returns the device back. So let's see if this still works. Okay, that doesn't work. Okay, because I have a comma in the device. Where is it? Over here, right? Because these are now buddy, method members on the device, right? So we can't have a comma over there. And what else? Okay, we still have commas at 65. Yeah, over here. So we don't need those commas anymore. And the same thing for the light bulb. Right? Okay, so this is sort of like an alternative approach. And okay, well, what do we have? If your expression does nothing in statement position. All right, so I wanted to print it out. So over here, we want to print it out, print out. Right? So now, okay, now it works with the light bulb, and now it should also work with the TV. Now, this was just the first step because we're still passing functions, pointers to functions around. And in object-oriented program, we really don't want to have that. This is why object-oriented languages, they have this thing built into the language. This thing called is called a dynamic dispatch. So what we're going to do is we're going to go to the device. And by the way, notice that these guys are not being called. So actually, instead of doing this, let me do this. Let me surround it with a curly brace like this. So I just indented it differently, right? So because this is never being called, we're gonna do actually, hold on, let me here, and here. So instead of all of this, we're gonna do system.error. I'm just basically gonna throw an exception, and we're gonna say please assign a value first, which is not really beautiful code. Now we see this exception because I made a mistake, because I'm just returning it, but instead we want to return a function that doesn't take anything, but returns in this case an int, in this case a unit, in this case a unit, right? So because we never call the device in this state, this never ends up happening. Right, but it's still not type safe. It's still not beautiful. So we want to finally start to getting rid out of those functions. So instead of this, right, we want to have the regular syntax. So we want to have something similar to the TV. So instead of you know, this whole stuff, we're gonna actually go to the TV, and we're gonna let me just copy that. Let me just copy that, and I'm gonna paste it over here, and I'm just gonna replace the buddies with this. So turn on is gonna do this, turn off is gonna do this, and watts per second is gonna do this as well. So now we're gonna remove these. Right, so basically a device now actually sort of looks like a TV, and we can have it as a val, as a val, because, you know, on the instantiation it will throw this error, so it also has to become a def like this. So now, instead of having functions defined on TV and on light bulb that are called toDevice that will construct this device, we will actually be able to say in the language that a light bulb and a TV, that they are a device, and we do this by doing this. We say extends a device, right? So now we don't need this toDevice thing, right? And we're gonna do the same thing. A light bulb extends a device. Yeah, so this literally means that a light bulb is a device, and the same thing for the TV. Okay, so a TV is a device. So because they are already devices, let's remove this toDevice thing. Because they're already devices, we don't need to do this, okay? And the thing is that we also need to say, okay, so a TV is a device, and we need to override whatever a device was doing, right? So the device was doing, you know, was throwing an exception. So now we have to say override. And now we're gonna say override over here as well. By the way, notice a teeny tiny thing. We're gonna have you know, a bit more details in the next video, that it is possible to override a def with a val. So on the device, actually let me move down this device. It's so far away from the devices. Let me move it down to over here, right before we did the TV. So a device has a def watts per second, but we're actually overriding with a val. Okay, it's not possible the other way around, and we're gonna have all the details in the next video. So let's see if I made some mistakes. Yeah, I did. Okay, so I made 31. So we go to 31. Watts per second is just an integer now, so it's not a function. So let's have this, and everything works now. So this is the proper solution for the first time, right? So we have an energy meter that takes one thing as an argument, and we can pass it a TV, and we can pass it a light bulb, and nowhere we're passing pointers to function around. And this is what the object orientation actually gives you. It gives you this so-called subtype polymorphism, which means that a type can have different forms. So a device can be a light bulb, and a device can be a TV. It's called subtype polymorphism, and it's also sometimes called a dynamic dispatch, right? So the same as static dispatch, we now have a dynamic dispatch, and dynamic means that the compiler implements this static dispatch for us. So at the compile time, it tries to dispatch on the type to figure out the type, and if it can't, instead of throwing an exception saying not a device, it's just not going to compile. Okay, so we're by the end of this slightly longer video. The only other thing that we need to do is there is a way to get rid of those system errors. So there is a way to say, okay, it should not be possible to create a device on its own. You can only create devices by extending them first and then creating instances of those classes. So right, so we have a light bulb that extends a device, so we can create light bulbs, but we shouldn't be able to create devices. And by doing that, in order to do that, we can prepend an abstract keyword. So we can say a device is an abstract concept. So you can never do something like this. Val device equals new device, right? So this is not going to compile now. Actually, let's demonstrate that. Let's put it down like this, and now it's going to say class device is abstract, cannot be instantiated. Okay, but we don't want to instantiate, right? We want to instantiate a TV or a light bulb, right? So now, because it's abstract, we can simply remove the buddies, right? So everything from the equal sign, right? Those things, we can just remove them. Right? So a device is an abstract thing, right? So we just have the signatures, but there's no implementation. And the compiler will make sure that the implementation is provided. So there is no way to call the device anymore in this wrong state where the variables that were keeping track of the pointers to functions, that there is no value assigned to them yet. There's no way. The compiler will make sure that you implement those functions. In fact, let's demonstrate that. So if we go here, for example, and we comment out turn on, we're going to see class TV needs to be abstract since method turn on in class device of type is not defined, right? And by the way, we can also, because the device is abstract now, we can also remove the override keywords. But I highly suggest you not to do that because, so if you just remove them, it's still going to work, right? But if you keep them, which is a bit more to write, then I'm sorry, like this, right? So if you keep it's a bit more code to write, but at least now it will protect you from things like this. So if you thought that you were overriding something, so let's do override def, do something. Print line. I'm doing something. So if we have the override keyword, it will tell you, hey, this is probably a mistake. Method do something doesn't override anything, right? But if you leave it out, then it will be fine. And this might be a mistake. It's not always a mistake, but occasionally you would do something like you would do turn off, right? And for whatever reason, you're gonna have a 0 here. It looks like turn off, but it's not, right? So it's so now if we have an override, well, now it's actually gonna complain that yeah, it says method turn off overrides nothing, right? So basically, always leave this keyword override. We're going to discuss all the details in the next video, but let me leave you with a few more things. First of all, you can only extend one class, right? So if we had another abstract class over here, right? So let's have another abstract class called, I don't know, entertainment item, right? We can't go here and say class TV extends device and then extends entertainment item. We can't do that. First of all, because the syntax doesn't allow it, right? The actual syntax is, there's a way to so-called mix in a few things, but you can't mix in more classes. So the proper syntax is to say with, but it's still not going to work, right? Because it's still going to say class entertainment item needs to be a trait to be mixed in. So a trait is just another keyword. Basically, it's very similar to an abstract class, right? So if this is a trait now, then it's going to work, right? Okay, we still have the turn off. Oh yeah, I still kept the turn off. Let's remove the turn off. Right, there we go. So so now it works. And in fact, we can also turn the device into a trait. There are some subtle differences between traits and abstract classes, and we're going to discuss them in some other video. As of right now, if you have something abstract, start with a trait, and only if you run into issues, convert into an abstract class. And also you can mix in as many traits as you want, right? So you can have, for example, the trait called expensive item, and you can mix it in as well as expensive item, right? So it's still gonna work. Okay, the very last thing that I'm gonna say is that the JVM as most environments and Java and Scala as most languages, they implement the so-called nominal type system, right? So it's a type system that distinguishes types based on the name and not on the structure. So for example, if I actually let me revert those things. So we don't need this. We don't need them. So we're just going to extend the device. Okay. So if I copy the structure of the device, so if I copy the device and I put in over here something with exactly the same structure, but I give it a different name, right? And now I say, okay, the TV is now not a device, but it's a gadget. Then something, oh yeah, it's, I just got scared. It still compiles because we're not using the TV. Let's go and use the TV over here, right? So now it's going to say, okay, I found a TV, but I required a device. So the energy meter still says that it wants a device, and now the TV is not a device anymore. It's a gadget. So even though it has exactly the same structure, the energy meter can't do anything with it. Now there is a way around this. There is a way to imitate structural type systems, which are very rare, by the way. I'm going to show you how. But this is more like just a treat. You almost never have to use it. In fact, in my 8 years of Scala, I never had the situation where I really need to use it. So the use cases for what I'm going to show you are very exotic. But I'm still going to show it to you. So what you can do is you can go over here, and instead of trait or an abstract class, we're just going to create a type alias for the structure. So we're just going to create a structure, type structure equals. And then we're just going to paste the body, and we're just going to say, okay, everything that has a structure, is basically, you know, a structure. I call it structure. So now we can go over here to the energy meter, and we can say, we can pass it everything that has this structure, right? So now, even though the TV is a gadget and not a device, because the gadget has the same structure as a device, and the energy meter is fine with working with a structure, it's gonna work just fine. And now it tells us, okay, there are 3 feature warnings. Rerun with feature for details. So we need to do the similar trick as before. Remember, I told you that by the end of this video we're gonna have more flags. So what we need to do is, first we need to add -feature, right? And now we need to reload the project and do the run thing. Okay, so now if we go up, okay, let me let it finish. So now if you go up, it's going to say reflective access of structural type member method turn on should be enabled. So basically Scala warns you, hey, this is some shady feature, so only, you know, it's not for beginners. So it basically warns beginners that this is, you know, a fancy feature, and if you want to enable it, then you have to go and enable it explicitly by adding this compiler option, this one. So we're going to do this, copy, and instead of just saying feature, actually, hold up, we're still going to say feature, but we're also going to add yet another one, which is this one. So now if we reload again, reload, so now everything is enabled, and now we're sort of on our own. Now we don't have any warnings, and everything still works with a TV and also with a light bulb. Okay, so this structural type stuff is, again, very fancy, so please don't use it unless you're super sure that you actually need it. And also it is slower. It is using a concept called reflection, where at runtime the compiler tries to figure out the type and to call those functions. So it's in this case it's a safe reflection, because at compile time Scala compiler made sure that the types match, but the call to those functions happens through reflection, and therefore it's slower. So this is yet another reason not to use it. And by the way, before we were talking about everything, we can demonstrate the dynamic dispatch over here. So as of right now, we don't have any dynamic dispatch over here, but we could say that this is a device. And now at compile time, the Scala compiler will try to figure out what kind of device is on the right hand side. And I believe right now we would actually do structure, which is kind of crazy. I think this should also work. Yeah, structure. But that's it, another thing. So the dynamic dispatch happens every time where you have some subtype on the right, and you have some higher type, not higher type, but the base type on the left. And this happens over here, right? And if you don't do this, and by the way, by default, Scala infers light bulb. So by default, it thinks that it's a light bulb anyway. So now dynamic dispatch happens over here, right? So we're passing in a light bulb, but it actually wants a device, or in this case, a structure. Technically, what I just said right now, it's not entirely correct, but because dynamic dispatch actually happens on when you call the methods. So it's over here. So whenever you call device.turnOn, at this point it tries to figure out which kind of device it is, and dynamically dispatches to call the subtype method. All right, so this video was a bit long, but I really hope that it helped you to really understand how dependency inversion is implemented in a pure object-oriented way. In fact, we're probably going to have a video soon about how functional literals are implemented, because it turns out that they're implemented in a very similar way. All right, it's been Vlad. Like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.